Okay, so this is the third hour of Physics 1A, section 1617 for April the 6th. And we've just finished discussing how to solve a problem involving an inelastic collision. And yeah, we have a few more problems that we can solve here, but I really want to start talking to you guys about the different types of collisions we can have. And in particular, discuss a special type, which is called elastic collisions. So, okay. So you can break down collisions into kind of like two categories. You've got what are called elastic collisions and inelastic collisions. They sound very similar. Inelastic. Okay. Elastic is like, bouncy. Okay. So an elastic collision is a collision in which no kinetic energy is lost. Or no kinetic energy. Nah, that's a better way of saying is that kinetic energy is conserved. And by contrast, then an inelastic collision is defined as one in which kinetic energy is not conserved, and it's converted into some other type of energy. All right. So inelastic collisions cover the vast majority of collisions. Elastic collisions can really only occur if the force that's involved in the collision is a conservative force, meaning it needs to be something like a spring, or you need to have like a force like the force of electricity or magnetism that can allow it to not convert the energy over. Okay, so examples of this are collisions in which the objects basically don't touch each other. Okay, so if I, for example, have a proton, okay, and I have another proton, both positive, so that they feel a force that that works against them. If these two objects are going to collide with each other, then the collision is going to be an elastic collision because technically these two things will never actually touch each other. Okay. Any collision in which the objects don't actually touch each other is going to be an elastic collision. Okay. And another example of what's close to an elastic collision is collisions between billiard balls. Okay. One other possibility, let me move this down just a little bit. One other possibility for, oh man, that was weird. Why did it interact like that? Look, I just want to click here and then I want to, what do I have to do like that? No. Whatever, we'll just do it like this. Okay, so elastic billiard balls, right? Another example of this, and this is something you'll probably see in some of your homework problems, is if you have like a surface and I have an object, and one object has like a spring on it, and the other object has like a spring on it, like this, and they're moving towards each other like this. This could also be an example of an elastic collision where they collide, the energy of the collision gets stored in the spring, and then it gets pushed. Will there be office hours on Wednesday and Thursday then of this week or next week? I probably won't have office hours during spring break, but I'll be around. You can ask me questions if you want to. Will there be office hours this week on Wednesday and Thursday? Yeah, for sure. Okay. Elastic collision, kinetic energy is conserved. An example of where this could occur is if there's a spring, and the spring can store some of the energy. In that case, you can also get an elastic collision. Okay. Yep. An inelastic collision covers basically everything else. This is all other collisions. So this could be collisions between two cars. If you have two people that are maybe pushing off of each other on skateboards, as I said earlier, it could be any other type of collision is what we call an inelastic collision. Now these ones, elastic collisions, we can handle using kind of a special way of handling it. All right. So suppose that we have a system like we had before, where you've got. I'm going to elaborate on elastic collisions here. Suppose you have a situation where you've got ball one, ball two. They move towards each other. This one has a velocity v1. This one has a velocity v2. Oops, v2. They collide so that this one moves in this direction with a velocity that we call v1 prime, and the other one moves in the opposite direction with a velocity that we call v2 prime. Okay, that's our elastic collision scenario. These could be two electrons or two protons or something like that. What we can say for this system is that the momentum of the system initially should be equal to the momentum of the system after the collision if we sum up all of these. In addition, we can also say that the kinetic energy before the collision should be equal to the kinetic energy after the collision. Okay? Again, if we sum up all of the possible kinetic energies. In an elastic collision, the kinetic energy is conserved. So, the left side equation for this one here is going to be something like the mass of ball 1 times its velocity plus the mass of ball 2 multiplied by its velocity. And I realize now that I definitely will not have enough room for this. So what we'll do is just select this. Oh my god, what is it doing? I just want to select. There we go. Let's move this over here. So this should be equal to m1 multiplied by v1 after the collision plus m2 times v2 after the collision. And then over here, we're going to have kinetic energy conservation, right? So that's going to say, move this over a little bit, 1/2 mass 1 times velocity 1 squared plus 1/2 mass 2 velocity 2 squared. And then this is equal to 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. Okay? What we're going to do is we're going to kind of rearrange these equations in the following way. So I'm going to move all of the terms with m1 onto the left-hand side. And I'm going to do the same thing for the terms with m2, but on the right-hand side. So this equation is going to become m1 times v1 minus v1 prime, and this should be equal to m2 multiplied by v2 prime minus v2. Can you guys see what I did there? I'll stop for a second and yeah. All right. We're going to do the exact same thing over here, except the things are squared and the 1/2s are all going to cancel out. So we're going to get v1 squared minus v1 prime squared is equal to Can you guys all see what I've done there? Does that all look right to you? So now what we're going to do is we're going to take this equation here. We're going to put it underneath this equation here. And we're going to divide these guys. We're going to divide that equation by the other equation. I'll let you guys think about this for a second, but if I have something like this, like I've got v1 squared minus v1 prime squared, and I'm dividing that by v1 minus v1 prime, can anyone tell me what this is equal to? What do you guys think? What's that equal to? Yeah, that's right. And if it doesn't immediately become obvious to you why that's the case, the numerator is a difference of squares. So we can write it as v1 minus v1 prime multiplied by v1 plus v1 prime. And we're dividing that by v1 minus v1 prime. So that term right there cancels out. That looks awful. So basically that whole term cancels out with that term, and you're left with just this. Okay? So, this whole thing here is basically going to reduce down to this. On the left-hand side, you're going to get v1 plus v1 prime, and on the right-hand side, you're going to get v2 plus v2 prime. the sum of the velocities before and after for ball 1 in an elastic collision is equal to the sum of the velocities of ball 2. Normally the way that this is written, though, is like this. If I take v1 and I subtract v2, okay, this should be equal to basically v2 prime minus v1 prime, right? But we can also write that in a different way. I can factor a negative sign out, and I could write it as v1 prime minus v2 prime. And this equation is an equation you can use when you're solving problems that are elastic collision type of problems. It only works for elastic collisions, though. But it's an equation you can use in place of having to use this one here. So what you do is you use your conservation of momentum equation. That's equation 1 that you'll use, and you use this one here if you want to solve problems that involve elastic collisions. It's a very useful kind of thing. Now, what this equation actually states is kind of interesting. If you think about what v1 minus v2 is, okay, like let's pick some numbers. Like suppose v1 was 20, and suppose v2 was like negative, doing it again. Suppose v2 is like negative 30 or something like that. If I do v1 minus v2, what would I get? I would get 20 minus negative 30, and I would get 50. What is that? What does 50 meters per second represent? Does anyone know? What does that 50 meters per second represent? I've got a ball that moves to the right at 20. It's about to collide with the ball that's coming towards it with a speed of negative 30, right? And I get the answer 50 from the right-hand side of this equation. What does that represent? The difference between the velocities. Accurate statement, but that's not what I'm looking for. What does that represent? There's a more general thing you can describe that as being. I'm driving on the road in a car that moves at 20 miles an hour or something. A car approaches me at 30 miles an hour. It's the relative velocity, exactly. This is the relative velocity. We call this the velocity of ball 2 with respect to ball 1, right? And the left-hand side of the equation is negative the velocity of ball 2 with respect to ball 1, right? But this is after the collision. Does that make sense? So what this says is the velocity of ball 2 as viewed by ball 1 before the collision is equal to the negative of the velocity of ball 2 with respect to ball 1 after the collision. Does that make sense? The relative velocity before is equal to the relative velocity after, but they're opposite in signs. That's kind of an interesting statement about what happens in these kind of collisions. Now, we can think of a really simple example here, where suppose that this is 50, then this has to be negative 50, right? What if we set it up so that we just change the velocity of ball 1, instead of being 20 and negative 30, what if we just shift our reference frame and say ball 1 moves with a speed of 50 meters per second, and ball 2 moves with a speed of 0 meters per second? It doesn't change anything, right? It doesn't change anything at all. It's just the same. I mean, we just shifted to a different reference frame. So then what we would know, if we did this, is that I would say v1 prime is going to end up being equal to 0, and v2 prime is going to end up being equal to, what, negative 50, right? Does that make any sense at all? I switched these, didn't I? I would have wanted this to be my... It'd still be the same idea. Suppose ball 1 was moving at 50, and ball 2 is moving at 0. Then after the collision, ball 2 would have to move. It wouldn't be negative, it'd actually be positive, right? We can see that in our... I want to choose eraser, but I don't want you to switch. Okay. This is what would happen. And we can see that pretty easily on this lab thing here. So if we take... if we make the masses of the balls equal to each other, and we make it so that one ball moves, let's say, with a speed of 2, then what happens is that it gives that speed over to the other ball, right? If they're moving towards each other at 2, then they move away from each other at 2, okay? We can also make it so that, let's say this one's -1. What's going to happen after this collision? If this ball is moving to the right at 2 meters per second, and the other ball is moving to the left at -1, what do you think is going to happen when they collide with each other? What does this other equation tell us is going to happen? This one here. What's v1 minus v2 in this case? v1 minus v2 would be 2 minus -1, so it's +3, right? So watch what happens when we do this. I would argue that they're going to exchange velocities. You see that? The relative velocity before the collision is +3. The relative velocity after the collision is going to be -3, right? Which is another way of saying that they're just going to switch velocities. Pick any numbers we want. We can make this 5. We can make this one -2. And again, they're going to switch velocities here, basically. You guys see that? The fast one starts going slow, and the slow one starts going fast. Okay. So that's an elastic collision. You get this extra equation you can use right here. Okay. Okay. So I don't think the example I want to use for elastic collisions, I don't think I copied it onto here, so I may need to actually grab that real quick. Here. So it's this one. The problem I want to do is this one. You could really do either one of these, honestly. Let's do this one. This one's kind of more fun. So this is the problem we want to do. I'll put it into the document too, so you guys can have closer access to it. Paint. That's not what I want to do. Okay. So in this problem, what we have is the fission of uranium nuclei in a nuclear reactor produces high-speed neutrons. Before such neutrons can efficiently cause additional fissions, they must be slowed down by collisions with nuclei in the moderator of the reactor. The first nuclear reactor, built in 1942 at the University of Chicago, used carbon as the moderator. Suppose a neutron is traveling at 2.7 times 10 to the 7 meters per second, and it undergoes a head-on elastic collision with a carbon nucleus that has a mass of 12U. Neglecting external forces during the collision, find the velocities after the collision. Okay, so that's our system right there. The sketch looks really bad. We might draw our own sketch, but hopefully you can kind of read what it says. Yeah, we'll probably just draw our own sketch right here. So we've got a neutron. And we've got a mass, right? We have the mass of our neutron that's equal to 1 atomic unit. We'll use that as our units for this problem. It's going to collide with the mass of the carbon atom, which is going to be 12 atomic units. And so this one's moving to the right. Let's say that it has an initial speed that we just call Vn. And we have the carbon, and Vn is equal to 2.6 times 10 to the 7 meters per second. It's going to collide with a carbon atom, and the carbon atom initially has a speed that's equal to 0. After the collision, it looks like the neutron bounces off of the carbon atom. So the neutron is going to be going back this direction with some velocity that's going to be Vn, and we don't really know what that is. In addition, our other object is going to be moving to the right with some velocity that we'll call Vc prime. In fact, we should call this Vn prime too. And our goal is to calculate what these are. Two unknowns, so we need to do two equations, right? The two equations that we're going to use are going to be the initial momentum of the system. We're going to sum up all the initial momenta and say that that should be equal to the final momentum of the system. And we're also going to use the other equation that we have from right here that basically says if I take the negative of v1 prime minus v2 prime, that this should be equal to v1 minus v2. So in our equation, or sorry, in our problem, that equation is going to be negative of what we're calling vc prime. Oh no, we'll make this 1 will be 2. So vn prime minus vc prime should be equal to vn minus vc. So then let's fill these things out. For the sum of momentum, this is before the collision occurs. The only object that has any momentum here is going to be the neutron. So if we take the mass of the neutron times the velocity of the neutron, that's going to be the entire initial momentum of the system because this one starts off at rest. And then for the final momentum of the system, this is going to be the mass of the neutron multiplied by its velocity after the collision, so v neutron prime, plus the mass of the carbon atom. It's carbon nucleus. I keep saying atom. It's just a nucleus, right? Yeah, carbon nucleus. So mc, and then the velocity of that nucleus prime. These are the two equations we want to solve. We could have used kinetic energy if you want to. Like, that's an option. But this is easier than using kinetic energy, I guess is mostly what I'm saying right here. All right, we know that VC is 0, so this term right here is 0. And so what we end up getting is basically that, so we know what Vn is too, right? So we're going to put in here negative Vn prime plus Vc prime needs to be equal to Vn, which was given in the problem, right? So what we can do now is we can isolate one of the variables. So what we'll do here is we'll replace Vc prime and see that Vc prime should be equal to 2.6 times 10 to the 7 meters per second plus Vn prime. That's what that equation tells us. And we can use that and plug it into this equation here. So we have Mn, Vn, we know what both of those are, is equal to Mn Vn prime plus mass of the carbon nucleus multiplied by 2.6 times 10 to the 7 meters per second plus Vn prime. Then we start to kind of write out what we've got. So we can isolate Vn prime like this and distribute out the MC through here. And you get MC times 2.6 times 10 to the 7. That's a point right there. And then we can solve for Vn prime. Does it make sense what we're doing right here? We're going to end up getting Vn prime is going to be equal to Mn Vn minus MC and then all of this divided by that. And then we just plug in numbers. So Mn was 1 U. Vn was... Oh wait, it's the same as this, isn't it? Yeah. So I guess we could actually do 1U minus 12U. And then that's multiplied by 2.6 times 10 to the 7. And then we divide this by 1U plus 12U. And so we're basically going to be getting like 1 over 13. No, not 1 over 13. It's going to be 11 over 13, right? So we get... okay, so it's 1 minus 12 divided by 13 times 2.6. So you end up getting negative 2.2 times 10 to the 7 meters per second, and that's Vn prime. And then Vc prime is going to be equal to 2.6 plus this. So what's left over? 0.4. So something like 4 times 10 to the 6, I think. And that one's going to be positive. And writing on the corner, I'm sorry, it gets kind of sloppy down here. So there we go. That's the velocity of the neutron, much faster because it's smaller, right? And this is the velocity of the carbon nucleus. Still pretty fast, 4 million meters per second. Does that all make sense? Does anyone have any questions? One thing I want to mention is that I didn't mention this before, but this specifically is for one-dimensional. So like what we just did, elastic collisions. There's going to be a similar equation that we can develop, but it's a little bit different when we talk about two-dimensionals. So, okay. Do you guys have any questions? Should we start talking about two-dimensional collisions now? So two-dimensional collisions, okay? And we'll do a problem with this. These are collisions in which you have the following situation going on. You could have something where like maybe a ball is going to the right and it collides with another ball that's going in this direction, okay? So that if they hit each other, what's going to happen is that upon impact, the balls are going to kind of go off in different directions, right? So after impact, what might happen here is that maybe the first ball, okay, maybe going off at some kind of an angle like this. This could be ball 1. Sorry, I'll make that a little bit bigger. So this could be ball 1, and due to the fact that it impacts a ball like this, but it has some forward momentum already, ball 1 might go off in some direction like this, and ball 2, upon hitting the other ball, might go off in some direction, maybe kind of like this or something like, no, it wouldn't go downwards. It would just get kicked to the right, right? But it would still go upwards. So ball 2 may be going something like, not quite the steep angle, but it would be going like this. That would be a two-dimensional collision. Now, collisions where both the objects are moving at the same time become quite complex. So normally what you do is you just simplify all of this and say, suppose I've got a ball that's moving to the right and it engages with a ball that's sitting still, then this ball is going to come along and the first ball is going to go off kind of at an angle like this, while the second ball is going to go off kind of at an angle like this. It's almost always possible, or it should always be possible, to rewrite a object that's moving upwards, just make it so that one of them is sitting still. And to handle these type of collisions, we just have to use the exact same equation we've been using. The equation was that if you add up all the momenta in the x direction, that it should be equal to the sum of all the momenta. Sorry, if you add up all the momenta initially, that it's equal to the momentum of the system after the collision. What we can do is we can basically cut this down into two equations, and we can sum up the x momenta and say that those have to basically sum to the x momenta before and after have to be the same. And we can turn it into another equation, which will be for the y direction, which is if I sum up all, not the forces, if I sum up all the momenta of these objects in the y direction, that the sum of all the y momenta after the collision should be the same. So x momentum is conserved, y momentum is conserved. That's basically what it says. Okay. We can also use this to solve some problems. And again, I have a problem for this, but I didn't put it into my document here. It's going to be before this. Sorry. I think the two-dimensional collision one is before this, right? Yep, here we go. No, that's not the one we want to do. I guess we could do this one, though. Yeah, this is fine. And I kind of want to do the other problem I have, though. I like the... Here. Stop it. There we go. Here we go. This one... This is the one I want to do. don't think I started recording this time. Oh, well. Oh, wait, I am recording. Oh, my bad. Okay, so this is the problem we want to solve. A 1 kilogram object, A, with a velocity of 4 meters per second to the right, strikes a second 3 kilogram object, B, originally at rest. That's this picture right here. In the collision, A is deflected from its original direction by an angle of 50 degrees, and its speed after the collision is 2 meters per second. Find the velocity of B after the collision. Is the collision perfectly elastic? If not, find the fractional loss in kinetic energy. So this is our system. This picture's pretty good. I wonder if I can just annotate on this picture here if I make it a little bigger. There's no labels for vectors, or the values there. So let's give these things some values. So we have a ball that's called A, that's moving with the velocity. And since this is the only initial velocity in the system, I'm just going to call this V initial. And that way we can avoid having to put some primes in here. We're going to call this velocity of ball A after the collision. I'm just going to call that VA. And instead of calling this one V prime, we're just going to call this one VB. Okay? So we've got a velocity VA, and we'll call that angle theta. Oh, no, theta is this one. So we'll call this angle, let's say phi. And yeah, we want to figure out what the velocity of ball B is after the collision. Does the setup of this problem make sense to you guys? Do you guys have any questions? Okay, so what we need to use to solve this problem is just basically what we just wrote down. We need to conserve momentum separately in the x and y directions. So we're going to sum up all of the x momenta before the collision and say that that should be equal to the sum of all the x momenta after the collision. And then we'll do the exact same thing for the y direction over here. Not forces. The sum of all the y momenta before the collision should be equal to the sum of all the y momenta after the collision. For the x direction over here, can you guys tell me what would be the x momentum in this system? Well, in order to do that, we need to define an axis. So we're going to define our axis to be positive x this way, and we're going to make positive y point up. What would be the initial x momentum of my system? I've got an object here. Its mass, here, let's put ma, and say that ma is equal to 1 kg. And what's ball B? 3, okay. Yeah, what's the x momentum before the collision going to be? Do I mind scrolling up? Sure. This one here. That one there. MAVA, yeah. So the x momentum before the collision is going to be the mass of object A. He means V0, yeah, okay. The mass of object A times its initial velocity. So MA times V naught. After the collision, they're going at angles, right? So really, we kind of need to draw a little bit of a diagram here of what's going on, I guess. You've got one vector that goes off like that. That's what we call VA. And this vector is going to have components, right? It's going to have a component that goes this way, and it's going to have a component that goes this way. And if this angle right here is what we're calling phi, then this is going to be VA times the sine of phi. And this is going to be VA times the cosine of phi. So in the x direction, I would argue that the x momentum of this object is going to be ma times the velocity VA, which we don't know, times the cosine of that angle phi, which we do know. And then we need to sum up all the x momenta. So we also need mb times vb, and then times the cosine of the angle that it makes, which in this case is theta, right? So for vb, you've got vb points this way, and you can break it up into one that goes this way and one that goes this way, where this is going to be vb times the cosine of theta, and this is going to be vb times the sine of theta. Okay? We don't know what theta is either, by the way. All right, so that's one equation. It has, we'll talk about how many unknowns it has in a second, but that's one of our equations there. Maybe we should say it. How many unknowns in this equation right now? How many unknowns do we have? 3, yeah? The unknowns would be phi, VA, VB. Okay, sum of momenta in the y direction then, before the collision, right? Remember, this is before, this is after. What's the sum of all the y momenta in our system before the collision? What do you guys think? What's the sum of all the y momenta before the collision occurs? Oh, sorry. Yeah, we know phi. My bad. My bad. It's theta that's unknown. This one's 50. It's theta that's the unknown. My bad. Thank you very much for that. Theta is what we don't know. 0. You're saying 0 for this. The sum of all momentum before the collision is 0 in the y direction. That's right. There is no momentum in the y direction. This object is moving purely along the x direction. Now, after the collision, though, we do have some components here, right? And so we would say if we sum up those, we're going to get ma times va times the sine of the angle for that one is phi, right? And then we have to add to that the mass of object b times vb, and then times the sine of theta. Okay? Now again, there's 3 unknowns, right? So, how you actually solve for this it's really up to you. There's multiple ways to do this. We have 3 unknowns, and we'd like to have another equation, but the problem is that if you look at option B right here, the question is the collision perfectly elastic? If we knew that it was perfectly elastic, we could use conservation of kinetic energy, right? And that would give us another equation. But we don't know that that's true, right? So we need to be a little bit, I don't know, tricky is the word, to figure out how we're actually going to do this. You guys have any ideas? How would you solve this? And maybe it's worthwhile, I don't like doing this very often, maybe it's worthwhile to actually put some of the numbers in here so we can actually see what's at stake. So MA we actually know, right? That's 1 kilogram. And I think we know V naught too, it's 4, right? And this is equal to, so MA is 1. We don't know what VA is. We do know what that is, cos 50, right? And again, we know MB though, right? MB is 3. Okay, again, you can see now which things are unknown, and we can probably write it to be a little bit clearer. 4 meters per second is equal to VA cos 50 plus 3 times VB cos theta. In this equation, we can rearrange to say that, oh, VA is given. Oh, this problem's too easy. I forgot VA is given. Yep. Let's plug that in too. There's actually a way to solve this, I'm pretty sure, without. So this one's given. This one was equal to 2, right? Thank you guys for noticing that. And then over here, what we end up getting is basically negative MA is 1. VA was 2. Phi was 50. MB is 3. There we go. I could probably clean this up a little bit here. I don't need to write this all. 4 meters per second equals 2 meters per second times cos 50 plus 3 VB cosine of theta. The other one's probably fine. Yeah, what do you guys think? How do we solve this? How do we solve for these unknowns then? What do we do? There's a lot of options. There's at least 3 different things I can think that you can do here. So just whatever you think is... Well, it is a system of equations. I don't know how that answers. Solve for VB. Is that what you want to do? Just solve for VB and plug it in to the other one? Yeah, that should work, right? Use elimination. That should work. Why don't you guys try to do it? Do it yourself. Try to solve them. It's not that hard. You just got 2 unknowns and you got 2 equations. Yeah, I realize now that this is not actually an unknown. Sorry for confusing you. I didn't mean to do that. So if you guys try to solve it, I'll solve it too. All right. I did elimination as you guys suggested. This is what I got. Do you guys agree? And if you need more time, let me know. I very easily could have made a mistake. It's much easier. I should have just done it on paper, honestly. I probably did leave the 3 out. Yep. That's right. Thank you. That's going to change all these answers, isn't it? So, right. This equation should have been divided by 3. Times 3? No, VB is divided by 3. VB is equal to 2 sine 50 divided by 3 sine 50. So that should have been a 3. There should have been a 3 right here, which the 3 over the 3 would have canceled. So this number down here, this should have been -2. So now I thought that answer was like impossibly large too. I was gonna go back and look. I'm glad you already saw what I did wrong. This would be -0.56. And if we take the arctan of that, there we go. That answer looks more familiar to me. This is going to be wrong too. And so is this one. So what I get from that is 29.4. And then down here, this will be -29.4. So we get that's what I got then. Does that look right to you guys? Do you get the same answers? Oh, good. That's good. Okay. Okay. Do you guys have any questions? I think these problems are really tricky. They can get even harder, too. If you change this to an elastic collision, well, we need to figure out, is it elastic? How would I determine, is it elastic or not? How do I figure that out? Oh, momentum's definitely conserved. We just used momentum conservation here. Momentum will always be conserved in collisions. It's something else. Kinetic energy, right? So we need to calculate for part B. We need to know what the kinetic energy initially is. So we'll say kinetic energy before. This is going to be 1/2 mass A times the initial velocity squared. And then we also need to calculate the kinetic energy after. I could go up a little bit here. It's a lot easier for me to write if I... Kinetic energy after is going to be 1/2 MA times VA squared plus 1/2 MB VB squared. So what is this? This is going to be, I don't want to write the numbers out. We're running out of time here. So it's 0.5 times MA, which is 1, times VA, which was 2 squared, plus 0.5 times 3 mass B plus, or multiplied by VB squared, which was 3.12 squared. So I get 16.6 for this guy. The unit should be joules. You guys check that. Make sure you get the same thing. Let me know if it's right or wrong. And the other one's going to be 0.5 times MA, which was 4, and then times V naught, which was 4 squared. And so that's 32. Did I do that right? You guys want to verify that also what you guys get? So this means that it is an inelastic collision because the energy has been lost. And if you want to find the fractional loss, that's basically 1 minus k after divided by k before. So that's k before after. This will give us the loss. So it's 1 minus, 16.6 divided by 32. And that's going to be 16.6 divided by this is going to be 0.48, which would be 48%. That's the fractional loss, the percent loss, however you want to say that. And that's a two-dimensional inelastic collision. Do you guys have any questions? Okay, if not, that's going to be the end of today's class, and we'll have next time we're going to talk about a few more types of, a few more instances of collisions, a few more examples, and we'll also talk about something called coefficient of restitution, which is something that we do in Physics 1A that you might not have seen in Physics 2A. So that's it for today. Thanks everyone for coming. If you guys have any questions about anything, I'll stick around and let me know. And yeah, that's all for today.